In this video, we briefly review Coulomb's law and see how it is used in describing the hydrogen atom. Two electrically charged particles exert a force upon each other. If the two charges are Q1 and Q2 and are placed at a distance r from each other, the magnitude of the force is F of r equals 1 over 4 pi epsilon 0 times Q1, Q2 over r squared. The force is proportional to the inverse square of the distance. So if you double the distance, the force shrinks by a factor of 4. This is called the Coulomb force, and the equation is called Coulomb's law. If the two charges have the same sign, say positive and positive, the force is repulsive. For opposite charges, the force is of course attractive. The prefactor, 1 over 4 pi epsilon 0, is called Coulomb's constant and is a result of the SI system of units, where the charges are in coulombs, the distance is in meters, and the force is in newtons. It is approximately 9 times 10 to the 9 Newton meter squared per Coulomb squared. The force is the negative gradient of a potential energy function V of r. F of r equals negative dV of r dr in our simple case. Integrating this using the force expression from Coulomb's law, we get the following potential energy function. V of r equals 1 over 4 pi epsilon 0 times Q1, Q2 divided by r, plus an arbitrary integration constant, which we neglect. Whereas the force depends on the inverse square of the distance, the potential energy only depends on the inverse of the distance. Let's apply this to the hydrogen atom, which consists of a proton with charge positive E and an electron with charge negative E, where E is the elementary charge. Let's place the proton at the origin in three-dimensional space. And then put the electron at some distance r. Since the proton is about 1800 times heavier than the electron, we can regard the proton as essentially fixed. The Coulomb force depends only on the distance between the particles, but not on the orientation. Therefore, it is better to use spherical coordinates, r, theta, and phi, instead of rectangular coordinates, x, y, and z, to describe the system. The potential energy function in this case is V of r equals negative E squared over 4 pi epsilon 0 times 1 over r. Let's plot this function. V of r is negative everywhere. For large r, it converges to 0. For small r, it diverges towards negative infinity. At 0.1 nanometer distance, the value of V of r is approximately negative 14.4 electron volts. This is the electrostatic potential energy function we need to use in a Hamiltonian if you want to solve the Schrödinger equation for the hydrogen atom. The Hamiltonian for the hydrogen atom is therefore h hat equals to negative h bar squared over 2me nabla squared, that's the kinetic energy term, minus E squared over 4 pi epsilon 0 times 1 over r. In summary, the Coulomb potential depends on the inverse distance between two charged particles, and we use this potential for describing electrostatic interactions between nuclei and electrons in atoms, which are quantum objects.